Ready?
And yes, I'm ready.
Hello, and welcome to the Blockchain Journal Club. I'm Perry,
And I'm Carlos.
and today we'll be talking about a paper called Difficulty Scaling in Proof of Work for Decentralized Problem Solving.
Yep. Nice, Perry. Thank you for the introduction. How are you doing?
Not bad, you?
Pretty good, pretty good. Okay, so yeah, why don't I jump right into it? Maybe quickly we'll say again that this is a Blockchain Journal Club. So every week we're going to pick a paper that's related to blockchain, and we're going to try to explain how it works a little bit. And then you and I will discuss it, maybe discuss related articles or potential like future directions that might be interesting. And yes, so I tried to write down a quick little explanation so that somebody who's not super familiar with all the blockchain concepts might be able to understand. And since this is an audio format primarily, I hope that you can have a mental picture going on while I explain. Do you see my screen, Perry?
I do.
Okay, perfect. So, yeah. So the reason we decided to start off the podcast with this article, which, full disclosure, comes from Perry and I and our colleague Alessandro, is not only because it's self-promotion, but also because I think it touches on a few points that are very important or kind of foundational for a lot of blockchain research. So really, if you're able to understand what's in this paper and related papers, you have a pretty good idea of the foundations of how Bitcoin and a lot of major blockchains work. Does that sound fair, Perry?
Sounds perfectly fair.
Very good. Okay. So, and the aspect of blockchain that it touches on the most is obviously the mining aspect. And it's probably the strongest contribution from Satoshi Nakamoto coming out with, decentralized cash systems is this, you can easily come up with systems that keep track of transactions between people. This is essentially a ledger. We have databases for that. A sends B 5 Bitcoin. We can log that in servers, and that's fine. But what the mining algorithms do is they allow us to sync this information across an entire network that doesn't have any special authorities governing it. So the more formally, maybe we can say is that in Bitcoin, you have miners, and miners are basically computers that are listening to transactions that are happening on this network. And they basically, at a time point, collect a bunch of these transactions, they check them, and if they pass certain tests, which are very basic things like, does the person trying to spend this Bitcoin actually have that much Bitcoin to spend? Are these valid addresses? Has this transaction been processed in the past? So there's simple checks. Once these checks are verified, then you can group these transactions into a block. And that's essentially a snapshot of all the transactions that are approved at a given time point. And then all we have to do is take that snapshot and append it to some data structure, in this case, a blockchain that keeps track of all the history of these transactions. Perry, feel free to stop me if you want to jump in with anything also.
So far, everything sounds perfect.
Nice. Okay, so that's nice, but the problem is nobody is actually governing this network. Nobody's looking at all these blocks that are being created by miners and saying, all right, this is the next block that we're all going to approve on. In other words, even though the network is happening spread out across the world, we still want one version of this blockchain to be the accepted one. So one history needs to be the true one. And in order to do this, essentially, we need to pick one miner's block to be the next block to be added to this definitive version of the blockchain. In order to do that, that's basically what the proof of work or mining algorithm does. So it essentially tackles three problems that come up in decentralized transaction networks. One is incentivizing members to participate in maintaining this ledger. Two is ensuring that everybody can stay in sync and up to date with the latest version of the ledger, and that there's only one latest version or one accepted latest version. And it also adds some security. So it makes it difficult for some miners to basically redo the history and sort of overwrite it, because it actually puts in a pretty strong energy and cost barrier into creating these blocks and having them appended. So if you were to try to undo a transaction that was already approved, you would essentially have to be doing a lot of computational work. And if the network is big enough, that can be so large that it's often not even worth it to do this. And you might end up just making more money by being an honest participant and just getting the rewards that you get from adding blocks. So I should have said that when you add a block, the network basically rewards you with some amount of Bitcoin. And that's really why people mine Bitcoin, is to get this reward. Yeah, so that's it. So that's the point of mining, and it's essentially a way to select the next block. And you can think of it as a lottery, where whoever solves a specific problem, or essentially someone is randomly selected to have the next block, but it's random proportional to a degree of computational power that you invest into this process.
And given that the transactions of the proposed block are valid.
Yeah, exactly. So yeah, we're assuming that a bunch of miners have a valid block at time step t, and then we say, okay, which one's going to be the next block on the history? And if it's invalid, this can be easily checked. You can just look at the transactions, compare it to the previous history, and say, this miner tried to throw in some crap into the blockchain. We kick it out. Okay, we don't include it into the definitive history. So in more specific terms, what happens is every miner takes his block and applies a function to it, which is called a hash function. And essentially, it's a function which maps data of any size to a fixed size output. So it essentially assigns a numeric value, say, to any kind of input data. So you can give the data inside of the block that you're working on to this function, and it's going to spit out a number that essentially looks random. So there's no real pattern to how it creates these numbers, which we call hash outputs or hash digests. And in a sense, it acts as what people call a pseudo-random function. So all outputs are equally probable, but deterministic. So if you were to rerun this function on the same input, you always get the same output. So okay, nice. We can essentially create a little bit of unpredictability out in this blockchain while still being deterministic. And then we use this to create a contest. So we allow the miners to hash their block together with a free parameter that we call a nonce. So essentially, it's just usually an integer or some small value that you append to your block, hash the whole thing, and that gives you a different output every time you change that nonce, that free parameter. And we say, okay, all the miners can do this to their block, and whoever's hash output is below some threshold, some numeric threshold, gets to be the next block in the blockchain.
One important thing of a hash function also is that it's not invertible, right? So you can't start off with the answer you want and reverse engineer what the input would have to be.
Exactly. So really the only way to win at this competition is by trying a bunch of different nonces or free parameters until you randomly get the desired value, which is usually just some number below some other number. So some number below some difficulty threshold. And because this function is essentially random, covering the output space uniformly at random, then the more numbers you try, basically the number of times you try this scales proportionally to your chances of winning this competition. So the people that invest more power in this process have a higher chance of winning this competition. So yeah, so another important property of this function is that once you have done this successfully, you can easily prove that you did it correctly. So anybody can then take your block, take the nonce that you said worked, apply the hash function, and check that I disconnected. That's horrible.
What happened?
I don't know. I think my internet died for a sec. But Oh, it still says it's recording. My
Okay.
audio is still going, so I think we're fine.
Okay, so what do you want to do?
Let's just keep going. Worst case, we have the audio. I don't want to restart this.
Let me just. How do I pause my Audacity? How do I restart it now?
Why would you restart it though?
How do I restart recording?
Oh no. Maybe like select like the end of the recording and press record. No.
Okay, no, it's working now.
You got it? You're still recording?
Yes.
Yo, never stop recording. Just keep it going. I can always just cut.
Okay.
Anyway, you're good. You actually continue the recording. You're not overwriting.
No, it's continuing.
Okay, sweet. All right. And I think the Zoom recording kind of resumed. Like it still says that I'm recording. So I think we're fine. Let's pray.
Sounds good.
All right. So sorry, some technical issues, but we are back. So at any time in the blockchain, all the miners are trying to do this. And then boom, one of them hits the number. Then all he does is, I need to share my screen. One sec. Okay. Yeah, so at a certain point, a miner will find a nonce that works for their block, and they can just publish this and say, look, I did the work for this block. You can check it yourself, run this hash function, and you'll see that it's below the difficulty threshold. So that means that I get to be the next person to add the block, right? And this difficulty threshold can be adjusted to basically control the speed at which blocks get added. So the smaller you make this number, basically, the fewer values are accepted as outputs from this hash function. So it's just less likely that you'll get the right one. And this is used in Bitcoin to make sure that blocks get added every 10 minutes. So the more people join the network,
so the difficulty threshold is determined by the blockchain to enforce this 10-minute block time, basically.
Yeah, exactly. Okay, so that's basically how Bitcoin mining works, and it's been working very well for over a decade now.
Very well at securing blocks.
At securing blocks, yeah.
Right,
so one of the criticisms is that that's pretty much all it does. So in order to run this hash function many times, you actually have to spend a lot of energy, which is good because, like we said, it makes it difficult for someone to redo all of that work if they wanted to change the history that we've all accepted. So that's nice. It serves a purpose. But it would be nicer if it served that purpose and another purpose, which could be to solve problems where they don't have the data involved doesn't have such a random behavior, but maybe is related to some real world problem. So we already have all these people interested in mining cryptocurrencies. Maybe we can leverage that interest to direct some computational power towards other problems. But that's not easy to do because this problem, so this hashing problem, that's basically a criteria for adding a block, has some requirements, has some properties that are pretty hard for any general problem to satisfy. So I listed here a few. Maybe I missed one or two, Perry, or didn't phrase them properly, but basically one property is that this problem can't be reused. So once you've done the hashing for one block with a particular sequence of transactions and a particular nonce, you can't just take that solution and apply it to another block. So the solution always depends on the current state of the blockchain. And this makes it really difficult for general problems to apply because usually the data in a blockchain is quite random. And we don't usually care about solving problems on random data. We usually care about things with specific patterns that usually come from other sources. So that's one big challenge. Another one is that the solution has to be easy to check. So easy in terms of computationally efficient. So someone can always just give me a block, tell me what hash function that, everybody agrees on the same hash function. They give me the block data. their nonce that they used, I can just apply those two things to the hash function and make sure that they get a good value. And these things run very efficiently. So the whole network can be doing these checks at any all the time, and it's not applying a lot of overhead to the network. Another one is what Perry mentioned, is that you can't really design your solution very efficiently. So you can't say, okay, I need a hash, I need a nonce such that the hash is going to be within a certain range of values. Doing that, going the other way, is super difficult. There's no known algorithms to do that. So usually the best thing that you can do is try at random. And this basically is a security guarantee for the network. We can always predict how much work it takes to produce a block on average. And the other thing is that the difficulty of the problem can be adjusted, which we just mentioned. Just by changing this threshold for the output values that you accept, adjust how many nonces on average you have to try for your block to be valid. So this lets us really control the pace at which the blockchain is updated. Is there anything else I'm missing, Perry?
And that's it. So yeah, so these are the key features I think you would want for a proof of work algorithm to work the way we want Bitcoin to work, I guess.
Yeah, exactly. So then people have come along since close to the beginning of these cryptocurrency blockchains and said, can we use a different problem maybe that where the solution, the output it gives us, which is just usually in the case of Bitcoin, just a random looking string, can that output be instead something more interesting or more useful?
Yes, yeah, so I guess the thing is, right now Bitcoin uses as much energy as a small country.
Yes.
Maybe a medium-sized country. So the point is, can we divert some of this energy into producing some sort of output that would be useful for people besides just guaranteeing the security of the network?
Yeah, exactly. The issue is that many real problems don't satisfy all these criteria, especially the one where we don't want reusability of the solutions, because if a solution is kind of independent of the data on the blockchain, then it can always just be used to fork the chain or overwrite the history much faster than it took to actually get the solution, right? So you can just copy over. If the nonce that you used for a specific block were to be reusable, then the next guy could just copy paste it and not have to actually do the work. So that's the main one that is a challenge. And some people have tried to replace the hash function with, I think one of the first ones was Primecoin, which said instead of outputting a hash value that's below a certain threshold, the challenge that you have to solve in order to add a block is finding the next prime in a specific sequence of primes. And this sequence of primes is dependent on the blockchain data itself. So the data induces a sequence of primes on which you can check what the next one's going to be. But again, so this is just one problem that might be interesting to some people, maybe not broadly interesting, and probably the subset of primes that it reaches is smaller than the actual set of primes that are interesting to people. So
yeah, so they try to find these Cunningham primes or something, right?
Yeah, Cunningham primes. And so yeah, the reference there is Primecoin by this guy Sunny King, right? Is it Sunny King? Yeah,
I think so. I guess the point is these Cunningham primes, we don't even know if they're useful for anything.
Yeah.
I mean,
and even if they were, they're just useful for one thing, right? So the whole blockchain is built around one specific problem, basically. So those are the two challenges there. Then people proposed blockchains that basically, on top of the mining, gave some of the users coins for solving certain problems that are more real world interest. So there's papers like CureCoin and Coinomy, which essentially still rely on the full Bitcoin procedure of hashing the blocks for the backbone of the system, but have a layer on top that basically rewards users for providing work that goes towards things like DNA sequence alignment or protein folding or any kind of optimization problem. which is completely on top. So it's using basically the cryptocurrency functionality to allocate rewards to people, but it's not replacing the mining, right?
Yeah, but so this one is centralized, right? I'm not even.
Koinomi. Yeah. So this one specifically has a way of kind of proposing DNA sequences to align and the validating them with special authority nodes and things like that.
But where do these extra coins come from? They're just like some stored coins in the blockchain, or they're just
Yeah.
produced?
Well, I don't know. I guess it doesn't matter, right? They could be minted. So yeah, there's usually a kind of like permission hierarchy happening in these types of things. And that's one big drawback. But there's still a lot of problems that we would like to be able to incorporate. So like we said, DNA alignment, protein folding, Ising lattice minimization. So solving, state systems of, what is it called? What is it? Atomic spins that you're trying to optimize
Yeah,
over? Yeah, there you go.
so quantum spins on a lattice. Say.
Yeah. Right. So yeah, that's interesting for some reason. And there's probably more interesting is finding the optimal choice of parameters for a machine learning model is also an NP-complete problem.
Hot topic, yes.
Yes. So I should have said there's a word for this type of problem that has these characteristics, and it's usually an NP-complete problem. So it's hard to design a solution. It's easy to check a solution is valid once you've generated it. So that works for the hashing problem. You can easily just hash it, see if the solution is what you want it to be, but you can't go from a solution to the proper like pre-image that gives you that solution. Okay. Mm-hmm. Yeah, so that's kind of the setting where we kicked off in 2017 of coming up with ways to incorporate scientifically interesting problems to the mining procedure. And we said, okay, well, it's going to be hard to find a problem or a set of problems that's interesting to include hard-coded into the blockchain that people will want to mine on, and also have these properties satisfied. So we said, okay, why don't we do something in between? So a kind of compromise, say, we're going to still require miners to provide this proof of work that's based on the Bitcoin hashing. Some people call it the Nakamoto consensus protocol. We call them classical blocks. So any block that's generated using this hashing procedure, we call classical. And then we say that we reward users not directly by giving them coins if they provide a solution, but actually by increasing their chances of successfully mining a block if along with their block they produce a solution to a problem that the network is interested in.
Yeah, so we magnify their lottery tickets, right? We give them more lottery tickets if they've provided a solution.
Exactly, that's essentially it. So this is just done by generalizing the standard Bitcoin difficulty update rules by saying instead of a single difficulty parameter, we introduce a second one that's somehow scaled against the original Bitcoin one that says if you provide a solution, you can post a block with this reduced difficulty, and then the network can just check that you hashed. You still do the hash, but your hashes are more likely to win the lottery if you also prove that you came up with a solution to an interesting problem. So that way you don't fully get rid of this really secure backbone of the hashing procedure, and you still incentivize people to sort of divert some of their computational resources towards solving any problem now, right? As long as the problem is of not scientific interest, but as long as the problem is basically NP complete, which means it won't be super heavy for the network to verify your solutions. And there's a huge range of problems that basically fit in this. We just went over them. The network would then decide, okay, we're going to work on DNA folding. And just through any kind of governance mechanism that already gets used in things like Bitcoin, they would say, all right, on this fork, we're solving these problems. Whoever produces the next best DNA alignment for the sequence gets to use a reduced difficulty in their block.
So this DNA aligning is a bit confusing because I think you need some sort of score also, right? But if we just take a simpler example of like the next prime, right? So if every time someone finds a bigger prime, that's like getting a better solution to this problem, right? Unless you want to show people maybe this DNA aligning thing.
No, that's just an example. I mean, you can always frame like an optimization problem as a decision problem by saying, okay, I'm not asking you for the optimal solution to this problem, but I want you to prove to me that there exists a solution better than this one. And by having this like target going in the blockchain, you can progressively sort of minimize any function you want, right?
Yeah.
And yeah, so I think maybe at this point we can just discuss what are the more like challenging aspects of doing something like this.
Yeah. So, well, first, maybe we should discuss. Okay, so the framing of the problem is basically any problem that we can say, does there exist a solution to this problem that's at least this good? So, yeah, maybe you can give the example. I don't know.
Yeah, I can whip out. I can whip out the paper. But I mean, people listening aren't going to see this.
Yeah. So the idea is, does there exist a prime that's bigger than some number n?
Yeah.
And the point is, well, the way to prove that there does is by producing a prime that's bigger than that number n, right? Then to increase the difficulty, well, you increase the number n and have to find a prime bigger than that new number n. So there's some difficulty adjustment here too, right?
No. I mean, not in our protocol, right? We don't have a constraint on the solution other than that it has to be better than. I mean, sorry, that's just a byproduct of the optimization, right? Like there's no control on the difficulty of the problem. It might be super easy to find the next prime, you know?
Yeah. So there's no control on the difficulty, but there is a. It gets harder over time on average, just because you get to the optimal solution.
Oh yeah, sure, but that's just like a byproduct of optimization problems.
Sure.
I mean, I don't know. Maybe some are like so solutions are uniformly distributed. I don't know. But the point.
But if there is a global minimum, then you expect it to get harder over time, right? To find that global minimum.
Is that okay? Is that the thing?
I think so.
Huh. What if? Okay, yeah, maybe. I don't know. That's not really like a factor for us, though. Like it could be trivial to find every solution, right? But the blockchain difficulty updating would still happen the same way, right?
Oh yeah, I don't mean the blockchain difficulty. I mean the solution to the problem can be trivial, right?
I think it can, realistically.
But then it's not NP complete, right? You can just
spam. Oh sure. You could spam, but you would basically have the difficulty would just adjust accordingly, right?
Yeah, but I guess one feature of the NP complete problem is that it's hard to find the solution, right?
Yeah, for sure.
So we need that feature in there.
Yeah, exactly. Yeah, so I guess that's cool. The only the main disadvantage is, however, that in order to prove that you have a solution, you have to provide it to the whole network. And then once the whole network sees your solution, then they could just say, oh, nice, I have a free solution to a problem. I can then just take it and use it to reduce my difficulty on a fork of this chain. Right. And if you do that for enough blocks or in a clever way, then you essentially like artificially improved your hash rate by some amount, because the difficulty for providing a solution is decreased. And so there needs to be some way to mitigate that risk.
Yeah, so basically in equilibrium, we expect the difficulty to mine a block classically or with the Bitcoin protocol is equal to the difficulty to mine it with this reduced difficulty plus the difficulty to solve the problem. But if you keep getting free solutions, you just automatically freely reduce your difficulty for no cost.
Yeah.
And so you can fork the chain and do a double spend, say, with less than 51%, just depending on how many blocks you have available with solutions, I guess.
Yeah. And in order to mitigate that, there has to be some layer on top, right? That says,
Yeah, so I guess we didn't focus at all on this. We just focus on this difficulty updating. But yeah, just like Bitcoin, I guess, you wait 6 confirmation times or 6 blocks before you expect your solution to be valid. or to be locked into the blockchain. Maybe in this protocol, you'd have to wait 10 or 15 or whatever X amount before you expect your transaction to be locked in.
Yeah. Yeah. So that's pretty tricky though to determine, eh?
Yeah, I think it's well, yes, it depends on the instance of the blockchain that we're looking at, I guess.
Yeah.
How many solutions are available, how spaced out they are, how far you want to go back, all this stuff.
And I think it would probably just come down to doing some tests eventually. You know, it would be cool if we could actually deploy the actual blockchain.
Or at least simulate like an attacker, you know?
Yeah. So for now, in the paper that we are publishing, which should be coming out in the Ledger Journal, I don't know, in a few months, is we simulated a network where miners are trying to solve the maximum clique problem on graphs. So find the largest possible set of fully connected nodes in a graph. And this is just a classical example of an NP complete problem. So we used it to show that indeed, like these problems naturally get harder and harder. Like the larger the solution you want to becomes, then it becomes harder and harder to find a problem. And so the new thing that we came up with 2020 and versus our 2017 paper is that we make the difficulty reward in terms of difficulty reduction sort of drop more and more as the problem gets harder and harder. So it's in the first version of our paper, we basically had a constant factor between the full hashing difficulty and the reduced difficulty. So even though the problem is getting exponentially harder as people find more and more solutions to it, the reward is not exponentially more beneficial. So eventually people would never be interested in trying to solve the problem when it gets to the stage where it's actually probably interesting to find a solution.
Yeah, so the reduced difficulty just tracks the classical difficulty, and it's just reduced by some constant factor throughout the evolution of the blockchain, right?
Yeah, so I can show the figure. Basically, you can see, for those of you watching on YouTube, you can see that if basically the line that shows the reduced difficulty over a blockchain's history follows with some constant margin the difficulty of Bitcoin in the original version. What we really want is something on the right where it actually keeps dropping and dropping until basically zero if no solution is found. And that raises, go on, Perry.
Sorry. So as the network, takes a longer and longer time between solutions, the understanding is that it's harder and harder to find a solution. So you should reward them with a greater drop in their difficulty to mine the next block. Yeah. As the solutions get harder and harder.
Yeah, because the logic behind that is, okay, if you're trying to find a solution that's really difficult to get, it means you've put in a lot of work, and then therefore you shouldn't invest that much work in actually just doing the hashing.
Right.
And that raises the next issue, which is sometimes the solution may be it may have been either saturated, like the current solution the blockchain knows about is the best possible one. And then you'll never actually know that you've reached that point. That's just a property of these optimization problems. It's never, you can never know that you found the best possible solution. So you can either keep trying for the rest of your life or exhaust all possible ways to solve this problem, which is usually impossible to do. Or you decide to move on to another problem, which is another thing where we're trying to think of ways to say, okay, how do we get the network to pick a new problem to work on without having any central authorities, which is one of those drawbacks of the first kind of NP complete solving blockchains, where they just had a special authority giving out problems to users and giving them rewards. We still want a decentralized way for the blockchain to move on to a different problem once it's saturated one of them.
And I guess this is a difficult thing because, if you want to keep it decentralized, there has to be a consensus on how to include a new problem. What we thought of is maybe the standard way would be just to fork the chain. Miners would decide on which chain they would want to follow depending on the problem, and then the people that follow, or the chain that has the most popularity, would be the new chain. With side chains developing, I guess, for people that want to solve different problems.
Yeah, I mean, to me that seems like a very cool and natural solution, though. I don't know why. So one of the reviewers said that hard forking is a really bad idea to do.
in general, he said.
Yeah.
But I think it's just a way of the blockchain evolving. Like hard forking is inherent in decentralized systems, it seems.
Yeah.
I don't know why you would remove that, but yeah, that's just a natural way I think of adding new problems, right? When the network decides that enough energy has been spent on a one problem, they can fork and work on a new problem.
And I think another interesting thing to look at is how that problem is actually chosen on a social level. Like you can't be like, oh yeah, I've spent my whole career sort of mining primes, and I think we should work on that because I already have a bunch of solutions ready to go.
Yeah.
I think like the network would have to say, okay, yeah, you know what, we're gonna try to find drugs for COVID-19, and
Yeah. So yeah, that
and
would be
then
cool, right?
yeah,
That would be super cool if you can like get some machine learning parameters from this kind of network to solve things that are like relevant in time.
Yeah, because then you can guarantee, or people would know that this is a recent enough thing, or it's well known that if a solution existed, it would be known, where you can actually have genuine like new work being added to the blockchain, right?
Oh my God, that's such a good idea. You're a genius.
It's all like everyone in my research group is talking about COVID stuff. Like my graph learning prof there, Will.
Yeah.
He gave a whole lecture today about using graph algorithms for solving problems in COVID.
No, but you're right though. Like if there was a solution, we'd know about it.
Yeah.
And we want to find a solution right now, and it's a natural thing to pick, I think, for a new problem, right?
Yeah.
That's a good idea. Like get the social thing in there,
For sure.
Predicting the election or whatever, current affairs.
And I don't see that as any kind of centralization though, right? Like any kind of update to the Bitcoin protocol is some kind of like topical current discussion that translates into a software update,
I guess the point though is that the miners get to pick which chain they want to mine on top.
Yeah.
So if they don't like a particular upgrade,
yeah.
If most miners don't like a particular upgrade, they can just, it gets rejected. So the miners get a final say maybe on how to update the network.
Sure, but that's fine, right? I can start a chain where I'm solving COVID problems, and you can start a chain where you're like doing icing minimizations, and people can be like, oh yeah, Perry's been working on this problem for years. He's like, he knows how to do this. He's hoarded solutions. And me, it's like, yeah, this problem came out yesterday. For sure, I don't have a solution. Let's work on this. And then people would mine on top of that,
Yeah, I guess the point is if the currency keeps forking, maybe it's not a useful currency, right?
Oh, yeah.
If you never know at what instance, you never know which chain to follow at a given instant in time, maybe it's not a good, it won't last as a good currency, I guess.
Oh, that's a good point. Yeah.
I guess the point is we've thought about this a lot mathematically.
Yeah.
But these social layers are a bit tricky, right?
For sure.
Yeah.
Huh. I mean, I'm sure there's like models for, forking chains and, studying how these happen at like a more meta level. It might be interesting to look at.
Yeah. Yeah. I mean, to get this off the ground, I think we'd have to do some studies like that.
Yeah.
And
or maybe just
implement it for real.
Just do a freaking Tangle, whatever.
A what?
No, a Tangle. No mining.
That's something else, maybe. Yeah.
I always feel like the answer is a Tangle, but I never know how.
Yeah. So, yeah, it could be. I mean, but it's weird because only very few projects are using Tangles, right?
Yeah, it's weird. I don't know. IOTA had such promise, and
they keep finding mistakes or whatever.
Yeah. That's a bit annoying.
What do we do? Yeah, so I guess that's the paper. Besides that, I don't know.
How long have we been going? Oh, 40 minutes. Not bad. I think that's really on target. Joe Rogan goes like 3 hours sometimes, though.
Yeah, we're no Joe Rogan, though.
No, I really want to model this whole thing after Joe Rogan. I really do.
From the beginning.
Yeah.
We should start wrestling or something.
Actually, I don't know if you thought more about this other paper. Maybe in the last like 5 minutes, we can quickly see what's up with this guy, Wei Li, 2018.
Yeah, we can talk about this paper. I still don't understand exactly how it works. I mean, you want to introduce it? I don't know.
So one paper that cited us and that kind of went under our radar was this paper called Adapting Blockchain Technology for Scientific Computing.
It's really recent also, right?
No, it's from 2018.
Okay, well, not really recent, but after our first paper,
It's
I guess.
ancient, yeah. We really got like the first paper doing this, eh? It's kind of crazy.
We started the wave.
For real. I mean,
I don't know.
there's no earlier thing that we could have cited, you know, other than like Primecoin and things like that. But I mean, everyone when that cites us says it completely doesn't work, you know.
We're the first at not working.
Yeah, which is fine. I mean, I think there has to be that guy that's the one that everyone says doesn't work.
Yeah,
I'm okay being that guy.
Yeah, for sure.
No, but so the idea here is you can actually take any optimization problem. So if you can think of if you think of an optimization problem as searching for solutions in a multi-dimensional space, then your proof of work could be to find a solution that is a local minimum over a subset of these dimensions. And
is it a local minimum over a subset or a global minimum over that subset?
See, I don't know. Okay, bounded local minimum.
It would have to be local because finding the global minimum even over a subset is probably very hard, right?
Yeah.
And it's hard to check also that it's the global minimum.
Sure. And I would imagine there's some kind of like current minimum that you have to beat, right?
Yeah, well, that makes sense. That's why I'm saying local minimum, right?
Yeah.
Because global minimum is probably impossible to find. To check, I should say.
Yeah, so the equivalent, I mean, I think the example that he gives in the paper is, imagine you're trying to solve the traveling salesman problem, which is basically you have a network and you want to find a path that visits every node in that network exactly once and doesn't go over any of them twice. So this is like a classic NP complete problem, where it's really difficult to actually find a solution, but you can check one easily. And he says, all right, let's just use this as our mining problem, and we'll solve the issue of adjusting difficulty by saying, if we want to make the problem really easy, then we let you only find a path over a subset of these nodes. So essentially, you're restricting your search space and making it easier to find a solution. Whereas if you were to run this on the entire network, then you would take a really long time to find a minimum. So that's kind of the difficulties adjustment that I gleaned off the paper. And then there's also the fact that the problem depends on the data of the blockchain, which I think is the coolest thing in this paper, where he says, okay, well, let's take the hash of the previous block. And since that essentially works like a pseudo-random number generator, then use that to pick which dimensions of this optimization problem you want to work on, or I should say like the dimensions of the problem that you want to accept as work. And in the network example, it would be like the hash of the previous block determines which nodes you work on for mining that block. So you can't really like predict what that's going to be. So you can't just reuse that solution and plug it into a fork of the chain, because it's just going to depend on the current state of the network.
Is there a way to update the problem?
I don't know, but if there is, then it would just be like the same as us, right? You probably have to fork and.
I'm not sure. Maybe the hash also gives you a new problem somehow, right?
Yeah, I guess. I mean, I guess it would be equivalent to saying you have a huge library of problems, and the network decides which one that current block is going to accept, right?
Yeah.
Which I think is something we thought about, though, eh? I don't know. I have a feeling we thought about something like this at some point.
No, yeah, we did, but I think the issue was, number one, are problems generated by blockchain useful or anything?
No, I mean like you have a list of 1 million problems, and your hash picks one of them every time. It's like a lottery over problems, right?
Yeah, but I think you always have the problem where what happens when these problems are finished?
Yeah.
And number one. Number two, what happens if they're not relevant? Like no one cares about them anymore.
Sure.
So I think you need some adaptive sort of thing.
Yeah.
Like COVID would never be in there because,
Well, I mean, you can imagine like, oh yeah, there's a protocol for updating this like list of problems or whatever.
Sure.
You know?
But that's right now our list is one problem.
Yeah.
So it's just a generalization, I guess, of what we've done already.
Yeah, so it is a search for local minimum. Adjust the difficulty by setting up the number of significant figures and values of delta. For example, we require delta star to have at least k significant figures. Okay, not sure what he means there. But yeah, I mean, I thought that was pretty interesting. I don't see like any major issues with it, to be honest, because you are kind of gradually optimizing over the whole problem, right?
But the thing is, what is the difficulty adjustment? Like, if it gets really easy at one point,
Mm-hmm.
or really hard at one point, you reduce the difficulty by making the optimization over less dimensions, over fewer dimensions.
I would imagine, yeah.
But that means then you can reuse the solution, right?
No, because it would be like you can have the same number of dimensions, but factorial number of possible combinations of those dimensions, you know?
I'm just saying, imagine it's one dimension.
Yeah.
Right? Someone down the line has solved for all the dimensions possible, right? One-dimensional things.
Yeah.
Or someone has solved for a two-dimensional optimization.
Yeah.
The two-dimensional optimization is valid for the one-dimensional problem.
Yeah.
So you can just pick that point, right?
Yes, but it's a local minimum, no? Like, couldn't it be that your optimization over 3 dimensions is worse than your optimization over 2?
Not over the same window, right?
Like if the 2 dimensions are a subset of the 3?
The two dimensions, yeah. If the two dimensions, exactly, yeah.
Yeah, but
Over
maybe
the same
like,
window. Over
yeah.
the same window.
Yeah.
So okay, there's probably a window adjusting thing also.
Yeah, I guess.
We should probably read this paper.
Yeah, it seems pretty interesting.
And relevant.
And very relevant. It didn't really get much attention though, weirdly enough. Oh, and I just wanted to point out another one. I didn't read it, so I don't think I can discuss it much. But I quickly Googled like, what people call this type of thing useful work, because it's not just, it's serving another purpose than just securing the blockchain. So if you Google that, there's kind of papers coming out from this year that say, oh, this one, yeah, AXChain. They cited us, yeah. March 31st, 2020. A secure and decentralized blockchain for solving easily verifiable problems. So they introduce a blockchain which can solve practical problems raised by users without greatly compromising decentralization or security. Oh, I like their wording of this, eh? We should use that. Without greatly compromising decentralization or security.
Yeah.
You still compromise it, but it's not greatly.
Of course.
I never thought of doing that. Oh.
Sure.
Under the reasonable assumption that the attack power does not exceed 1/3 of the total power. Okay, so their 51% becomes 33% attack.
1/2 of the total power can safely be used. Oh, wow. So they're saying if DR is 50%, then their ADA, then the 51% attack becomes a 33% attack.
Yeah.
I wonder how they figured that out. We should read this also.
Yeah.
I mean, smart contracts and virtual machines. Interesting.
Yeah.
They're going hard here.
They are. No, they went pretty hard. The thing is, yeah, I think there's things, I don't know if they do some kind of like solution hiding thing, right? That's another option, which is
like with ZK snarks and stuff.
Yeah, so you could imagine, instead of announcing your solution to the network, you instead emit a proof that you have a solution, which is essentially what ZK snarks do, which we probably will have an episode about soon enough. And essentially the network would be able to trust that you have a solution without you actually revealing it. So it would make it harder for someone to just copy it and fork the chain. And that might be like where we take our work in the future. Yeah, so let's look at this this thing. Anyway, I think we should end there. It's been an hour, almost an hour, 50 minutes.
Yeah.
Other than that, I think that's everything.
Thanks for presenting, Carlos.
No worries. Question: are there Cokes at the grocery store? Are there Diet Cokes?
There are Diet Cokes at the grocery store, yes.
Yeah. Okay. I'm thinking of going and just saying screw it.
You should definitely go.
Yeah. I saw people are lined up. You have to line up
outside. Yes.
Outside.
They're very safe and secure. About this whole thing.
Okay, so you line up and then that's it. You're in the grocery store like normal.
I think they make you like wash your hands before you go in. They like Purell your cart.
That's really stupid, eh? I mean, if you're infected, you sneeze once, and who cares that you washed your hands when you went in? You know, I don't get it.
No, yeah, I guess. Sure. Or you're
Like,
not wearing a mask, and if you're infected and you cough on all the apples,
yeah, you know, I have a bunch of masks. Turns out, I have a box full of masks.
you should solve them.
Yeah, and they say like they protect against influenza.
Nice.
Yeah. Oh my god. Anyway, okay, so we're gonna end it there. Thank you for listening. We'll probably be back next week with another episode, and hopefully Perry will have prepared a cool paper to discuss. Right?
Yeah, we'll figure it out.
Very good. Okay.
Thanks.
Thank you. Ciao.
Bye.
Um, let me hang up. Okay, I stopped my recording. Whoa. Okay, I stopped my recording. Where's our Zoom call? Oh, it's sharing screen.
Yo, how the heck am I going to send you this? It's going to be like 5,000.